Well, hi, we are the team of the group of Math 3. The team is integrated by Jose Hernandez, Juan Pablo Aguirre, and Carlos Rojas. Well, the problem we resolved, it was about the mass, found the mass of the Kepler 186f planet. We we have the density of the planet, and the question of the problem was which was the mass of the planet. Now we are gonna explain that in the video.
Well, we know that Kepler is a sphere, so we related the sphere of the planet with the spherical coordinates. We use the formula of spherical coordinates, and we related the density with the formula mass between volume. And in this way, we know that the differential of mass is density
times the differential
times
volume.
the differential volume. In this way, we plan the integral.
Yeah, so for the triple integral, which is the way we solve this problem, it was required for us to do it this way. We had to first know which were the limits of integration for our problem. So we know we have a sphere, and it is located in the XYZ axis in the origin. So we know first that we're going to have a triple integral of the density, as we have here, times the differential of volume. We know that the first thing we are going to, so then we plan, ignore this part, and we put it out like this. Then we substituted all the values, and then we got this, which is the density, this one, times the differential of volume, which is this one. And then so we knew the first thing we had to do was to understand which was the sorry, the limit of integration of sorry, of the raw value. So we know that this equation is going to go, the density will go from 0, because it starts at the origin, all the way to R. We know it because it says here. Then the differential of phi or phi, which is so I didn't explain this. So the rho is the radius of our sphere and how it changes, the distance of the radius from the origin to the all the way to the edge. Then the phi is it's the angle of aperture from the positive z-axis all the way to the negative z-axis. So it can have a maximum value of pi. And for this problem, we used pi because we are talking about the whole sphere, so it goes all the way to here. And then for the last, it was the differential of theta. And theta, what gives us is the angle of aperture that it gives to the whole circumference. If you can think about it as the angle between the positive x-axis and how much does it open. For this problem, we use again 2 pi because it's the whole circumference, because we want to have a whole sphere. So we have right now like the angle phi opening 180 degrees or pi, and then the angle theta, which opens the whole circumference 360 degrees or 2 pi. So now we have our problem planned out, and we can solve it. So that's the next step we did. We solved the problem, and for this is our equation. Well, this is the problem planned out as we saw previously. Then we started with the integration, following the steps. Here it is like really good explained. I think that we were very thorough with our explanation so that anything would be missed. And then at the end we got to this answer. This is the equation to get the mass of this planet. For this you would need the radiuses, the initial density, and with that you can get the mass of our planet. Thank you so much.